As usual, let's walk through a number of examples and exercise our understanding of the TCP's sender-receiver mechanism. So first scenario, very straightforward. We do have a data sender here. Host B is just sending acknowledgements. Host A here sends one packet starting from sequence number 92. And it's carrying 8 bytes of data. Therefore, the ACK should be carrying the sequence number 100. Now, this ACK packet is lost. Okay, so host A here waits until timer fires. And so the same packet is retransmitted. Finally, ACK comes back, and the next packet will go out carrying sequence number what? 100. Because the ACK number here is counting to the last byte plus 1. So 92 is the first byte. The last byte will be plus A subtracting 1. But ACK is adding 1 back here. Alright, so it's 100, and adding 1 back is also a way for the receiver telling the sender what is the next byte expected, what is the next data byte expected. So the packet coming out from the sender next is definitely going to be the same sequence number in the ACK received previously, right? 100. And the second example, again, host being the data sender, host B being the receiver. This time host A sends 2 packets back to back. First, starting from 92 and then carrying 8 bytes of data. So we know that the last byte is 99, therefore, the second packet starts from 100. And 20 bytes of data to be carried, so the last one is what? 119. And therefore, the ACK packet for the first one is last byte plus 1, 100. The ACK packet sequence number for the second packet is last byte plus 1, 120. Now, in this scenario, we are trying to demonstrate the strengths of using cumulative ACK. That is here. If one of the back-to-back packet that came in earlier, ACK is lost. But as long as one of the later one arrived, because 120 here is saying, server, you know what? All the packets before the sequence numbers are acknowledged, whether you receive an ACK packet for an earlier sequence or not. So up to this point here, sender host A here seeing, ACK 120, and therefore this packet and this packet both acknowledged. Okay. Therefore, there's no timeout is going to occur, and it's going to trigger sending of the next packet starting from 120. The third example scenario looks very much like example 2's, where we have a sender sending 2 packets back to back. Sequence numbers identical. Therefore, receiver here will be sending back ACKs, 100 and 120. The difference is this. Example 3 is to demonstrate a case where we have premature timeout. So that is saying the timer here, the interval is set very short. So timeout occurs before ACKs can come back. So first, timer occurred here. Therefore, timeout event in TCP sender's trigger. Therefore, we retransmit all the packets in the flight. So sequence number 92 will be retransmitted. Sequence number 100 will also be retransmitted. Okay. Now, ACK 100, ACK 120 will arrive later. Okay. So when ACK 100 arrive at the sender here, Y equal 100, that is the sequence number in the ACK. The same base at this point is still 92. So Y is greater than same base. Therefore, we change the same base to the new ACK number. And do we restart timer or stop timer here? Well, there is still outstanding packet, right? Which is this one. So we cannot yet stop the timer. So timer is refreshed here. So timer for 92 is restarted here because, hey, timeout occurred, retransmit everything, start timer. So there's already a timer ticking starting from here that is associated with sequence number 92. But here we restart the timer, and this timer is associated with send base 100. When ACK 120 arrive here, oh, okay, we need to change the send base because it was previously 100, and the Y is 120, bigger than 100, so change the send base, slide the window over. Do we stop timer or restart timer? Well, there's no more outstanding packet because there are no more getting called from above. Okay, so, yep, stop timer right here. The last point to make is this. When this data packet, sequence number 92, arrives at the receiver is going to see, oh, yeah, data byte up to 99 received. But the thing is, the receiver has already received up to 119. So those bytes are extracted and passed up above. So that's not extract 92 to 99 and pass it above again. So this packet will be discarded. And an ACK will be sent back. But what is the ACK sequence number? Well, receiver has already seen up to 119. So what is the next byte expected? 120. Good thing is this, when ACK 120 arrives at the sender, well, Y equal 120, which equals send base. Therefore, this packet is going to be what? Out of any of the three transitions, we ignore it. Sender does nothing. The second packet here with sequence number 100 will also arrive at the receiver, and it's saying that it's receiving from 100 to 119. This is going to be ignored as well because, yeah, 100 to 119 bytes have already been passed up to the application layer. So another ACK 120 is going to be sent back to the sender. And sender is just going to ignore it again. And that was example 3. Up until now, the TCP mechanism we were talking about is very, very simplified. Okay, the examples we went through is very much based on the simplified TCP sender. The actual TCP sender is way more complicated. We have not yet talked about possible retransmissions when the TCP sender receives duplicate acknowledgements. We have not yet talked about extra mechanism in TCP's RDT that supports also flow control and condition control. So these will be coming ahead. But these also, okay, explains in example 3. You'll see in the textbook, the authors will describe it this way. When send base 92 expires, the timer, we only retransmit sequence number 92. But if you recall back, in go back in, we will be what? Retransmitting from the smallest sequence number all the way to all packets that have been sent before but not yet acknowledged. So that should include sequence number 100. And that is what I was describing, explaining example 3. The fact in TCP is this. There's something a little bit extra here. When timer for send base 92 expires, the sending window size at the sender there is also reduced to 1. That is saying, when the timer expires, the sender is going to retransmit, but the window size is actually limiting it such that we can only send 1 segment. And 92 is the smallest sequence number, and this is the only packet can be transmitted. And that's why, if you look a little bit careful about the sender's finite state machine we were talking about, and here it is, let's ignore all these other transitions that are not relevant. So we're experiencing a timeout event here. Okay? The description in the finite state machine says this: retransmit not yet ACK segment with smaller sequence number. Now we read down the actions being taken carefully. You see, this is not in the pro form. So we retransmit just 1 segment and then start the timer for that segment. But this is really odd, right? So this is not really like go back N. This is not really like selective repeat either. This is in fact TCP's reliable data transfer mechanism trying to do a little bit of congestion control. Let's define more precisely what TCP sender does when there is a timeout event. Note that this is no longer the simplified TCP. This one is actually quite realistic considering congestion control. So in that, step number 1, the window size is dropped all the way to 1. As a result, we are only allowed transmitting one segment, a smaller sequence number segment. And then we're supposed to start the timer, but the timeout interval is set this way. 2 times the current timeout interval value. Then you go, hey, then what was the current timeout interval? Yeah, the current timeout interval is set here and here. In the transition where we get a call from above, and the transition where we receive an ACK packet from below. So you see the timeout interval are calculated this way. Yeah, this is what all those slides were saying, right? This is the equation we came up with. The average round trip time plus 4 times the deviation of the round trip time. Okay. Now, back to the timeout event. Setting the timeout interval to twice the current value. Oh wow. We were actually quite conservative here already, isn't it? That is what? Covering 99.99 something percent of all these RTT samples. And we are setting the timeout interval to twice that amount. That's way more enough. Why? The fact is this, window size dropping all the way to 1 and timeout interval being twice super conservative are both to address the congestion that's occurring inside the network now. Because when there's a timeout, that is also saying there's no more ACKs coming back. That is probably because data cannot go out. But TCP being a pipelined reliable data transfer protocol, oftentimes we're sending multiple of them out, right? If it's just, a sporadic drop, not due to congestion having consistent drops, then we should still be seeing, maybe a lower number of ACKs, or maybe seeing some duplicate ACKs, old ACKs coming back. Not that we get no ACKs at all and eventually run into timeout. Okay, so timeout is TCP's way of saying that, let's assume now the network is congested. Therefore, let's be very, very friendly to the network. Okay, let's try to slow down. By reducing the window size, because when the window size is small, you're sending very slowly. Let's also reduce the rate of retransmission, which is to increase the timeout interval. When it's twice that long, then we are retransmitting, the half speed. So both of these extra mechanism is to address congestion, which is to do congestion control. And you see here, in TCP, the reliable data transfer mechanism is somewhat mingled with the congestion control. And that's why you see in example 3, supposedly if this is go back N, then when the timer for send base 92 expires, sequence number 92 and sequence 100 should go out. But instead, only 92 goes out. So let's summarize up to this point the similarities between TCP's RDT versus a go back N. So we see similarity being what? Both of them are pipeline segment and both use cumulative ACKs, and there's only one retransmission timer and it retransmits timeout events. We've heard already, unique in TCP is this. The timeout interval is well defined. There's an equation, and there are good reasons just justifying the equation. And we only refresh timer on new ACK. and go back in, we actually refresh the timer even though it's a duplicate ACK. Also, in TCP, that's unique is this. Retransmission, if timeout occurs, we retransmit only one segment. Okay. So reducing the sending window size all the way to 1. And the timeout interval is doubled as well. Okay. So exponentially slow in case there are back-to-back timeout events. Now, there are more differences. First one, delay ACK. Second, fast retransmission. So these are the two extra mechanisms in TCP that's related to reliable data transfer that we need to talk about. And what's coming next, a big part, we're going to talk about TCP's congestion control more seriously.